Hello all, welcome again. So this week we would be on lab 11, which is on anti-derivatives. So far what we have seen is derivatives, and we have seen how to take a derivative on MATLAB. But this week we would be doing anti-derivatives, which is a step backward. So before that, I recommend all of you to go through all of this, and it's not that hard to just look at what it is. So let's get started. Now, anti-differentiation is the reverse process of differentiation. So when I say differentiate x squared with respect to x, it is 2x. That's the derivative. So if you want to go back, that is the anti-differentiation, you have to go to antiderivative. So we would be looking at how to take an antiderivative on MATLAB, and also look at few examples where you have a model and you have to take antiderivatives and solve for it. Okay, so let's get started with our MATLAB. Alright, the goal of these labs are to investigate the idea of antiderivatives in a graphical setting, then learn to solve applications involving antiderivatives using a computer. So before we actually start with our actual part of the question, we must know few basic things. So that is what I'm doing it there. Now let's say df over dx is the derivative, right? So f is a function, and if I take a derivative of that function with respect to x, that is what I have. And f of 2 is equal to 6. Why do we need this condition? You will know in a minute. All right. Now define two variables. One is x and c, where c is the constant of integration. So you will know why do we need that at the end. And my function with little f of x is x squared minus 4 times x plus 2. All right, that's little f of x. Now capital F of x is the antiderivative of the little f of x. So when I say antiderivative, it means you have to integrate a function. So to integrate a function, you will use command int parenthesis function and a variable. Similar to that we had in differentiation, we had diff of f of x comma x. Now we have int for integration plus c. So whenever you are taking an antiderivative, you will have a constant of integration at the end, because we know that the derivative of a constant is 0. So we don't know what we might have a constant at the end, but when we take a derivative of a constant is 0, then we go back to that equation. So that is why we always have a constant of integration at the end when we take an antiderivative. Okay, now so when I do that, that is my equation, that is the antiderivative. But next aim is to find my value of c. To find the value of c, we have to use that condition, f of 2 is equal to 6. So what I'm going to do is, I'm going to call a new line called my c is equal to solve f of 2 equal to 6 for c. So when I plug my 2 in my antiderivative equation, I should see 6 at the end. So when I say f of 2, this entire equation will have x is equal to 2. So that turns out to be 6. So I'm going to use solve command to solve for c. So when I solve for c, I have 22 over 3 as my constant of integration. Now my next step is to plug this back to my antiderivative equation. So that's what I'm doing here. F of x is equal to integrate f of x comma x plus my c, where my c is 22 over 3. Then this command is to check whether what I have is the same. So we know that our capital F of x is the antiderivative, and little f of x is the given equation, which is actually the derivative of a function. So if I take the derivative of that function and then compare it with the main function, it should be the same, right? So this is the antiderivative. So if I take a derivative, I should go back to that part. So that's what I'm doing here. I'm taking the derivative of f of x with respect to x, and I'm subtracting with little f of x, which is this equation. If those are true, I should see a 0 on my output screen. Okay, then how do I further check it? I'm going to do a capital F of 2. So if I plug capital F of 2, I have 6 at the end, so which is true. So which means my antiderivative, that one is correct in all aspects. So that's the basic idea behind taking an antiderivative. Now let's get back to the question. The example 2, what we have is the trajectory of a ball tossed upwards. Consider a differential equation which comes from Newton's second law of motion. So you must know what Newton's second law of motion is. So ball is tossed up and we have acceleration due to gravity, which is negative 9.8 meter per second square. So acceleration is y double prime. When you take a derivative of acceleration, you get velocity. When you take a derivative of velocity, you get distance. So that is basic physics. Then find the velocity v of t. So if you take a derivative of that function, you get velocity. So that's what I'm trying to show here. Y double prime is acceleration. So if you take a derivative, you can get rid of one prime. So you'll have y prime of t, which is velocity. Then the condition is v of 0 is equal to 50. Just like we had f of 2 is equal to 6, we have v of 0 is equal to 50 meter per second. Alright, so we must find a suitable velocity equation and then check at what time t I will have 0 at the end. Alright, let's get started. I'm going to define two functions, t and c, where t is time and c is, as usual, constant of integration. Now my acceleration from Newton's second law is negative 9.8 plus 0 times t. Of course 0 times t is 0, but we must not forget there is some time in the Newton's second law of motion where we have to use, because we are integrating with respect to t. So that's why I have 0 times t. Now velocity is the antiderivative of acceleration, so that's what I'm doing there. int a of t with respect to t plus a constant of integration. Now my next step is to find the value of c. So I'm trying to do just like I did before. My c is equal to solve v of 0 equal to 50 comma c. So I know v of 0 is equal to 50 comma c. I'm solving for c. I know what my c is. I'm going to plug that back to my velocity equation. Now, sorry. So if these two, if my antiderivative and the actual function is the same, then it's fine. So that's what I'm trying to show here. So diff, take the derivative of v of t. So if you take a derivative of v of t, you will go back to your acceleration, that is a of t. So I have a 0, then if I simplify with 0, then v of 0 is 50. I know that. Now how do you find at what time t I have v of t is equal to 0? So you have to simply use solve command again. VBA solve v of t equal to 0 comma t. Just run it. So at time 5.102 seconds, your v of t is equal to 0. You can simply check it. Simply plug t is equal to 5.102 in your v of t equation. So if you plug 5.1 in your v of t equation, the output has to be 0. So that is how you find t value which makes your function 0. And we have seen this earlier. This is not new. Okay. Then the third example we have is another model which is on rainy year. So scientists has developed a model which shows the change of water level at a reservoir for a period of 12 months. So we have an equation which is w1 prime of t, which is equal to sine 2 times t plus t cube into exponential part of negative t minus 2 whole square plus 1. So that is the equation, just like we had before. This is a new model which is on a rainy year, which shows the water level in a reservoir. Now we need to investigate this for few things that we must calculate. So I've divided this question. We are going to use the same idea to solve your assignment as well, so try to focus on this. So there are 3 steps you have to follow to analyze this. Okay, first step is to graph the derivative and look at the rate function by plotting the function w1 prime for the domain 0 to 12. So that's what I'm doing here. Define t and c, where t is time and c is constant of integration. Then that's my definition of a function. Then I'm going to plot this from 0 to 12, where 0 to 12 is months, 0 months to 12 months. So that is what I have right there. I have switched on the grid for easy access to read the graph easily. Then step 2 is to find the antiderivative and also the prime. Find the antiderivative and solve to find for c. So I'm going to call this as w1 of t, which is the antiderivative of w1 prime of t. So I'm going to use int w1 prime with respect to t plus c. Now the condition given here is w1 of 0 has to be 8. Suppose that also that we have known the initial water level. So let's say initial water level is 8 inches, which means the initial time is 0. So w1 of 0, let's say equal to 8 comma c. So that's my c. I'm going to plug that back to my little w1 of t. So that is what I have. Now just to check it again, I'm going to take the derivative of that function, which means the antiderivative function, and then compare it with the main function that I had before. So if both are same, I should see a 0 on the output screen. Then if I simplify that, I get 8, which was actually w1 of 0, which is 8. Now the third question is, this is not the exact question that I have on my manual, so I've just changed 12 to 10. That doesn't matter. Okay, so the question is, find the water level at the end of 10 months, which means my t is 10 months, and also find out when the water level was 30 inches. So you have to use 3 different commands. Let's say VPA W1 of 10, which is going to give you water level at the end of 10 months. So that answer is 37.79 inches, or if it is in inches, it is fine. Then I am trying to plot this just to check the second part of the question. Find out when the water level was 10 inches, which means you have to find time t at which the water level is 30 inches. So I'm going to say w1 of t equal to 30, and I'm solving it for t using VPA solve, and it turns out to be 3.5835. So that is the point. So this is the water level in inches, that's the time from 0 to 12 in months. So that is the point I'm looking at. So that point is 3.5835, somewhere between 3.5835. So that is it what we have. Then on the hint on the assignment is super easy. So the question is, I'm not going to say complete, I'm not going to give you complete answer. So the thing what you have to look at is w2 of 0 is w1 of 12. So if you solve for w1 of 12, you can easily solve the whole equation. So you just have to change the equation, and you just have to find what is w2 of 0 using w1 of 12. So find w1 of 12, which is actually from this part, and then plug it back to your main equation.